Hi, welcome back to calculus. We're going to be looking here at logarithmic differentiation. If you're taking my class, this is part of section 3.8 in your book. If not, well, enjoy the logarithmic differentiation. So I have some directions here, and then we'll jump into a couple of different examples that are going to be kind of fun. So I'm just going to run through these directions real quick, and then, like I said, we'll get an example on board, and hopefully it makes a lot of sense then. First, take the natural log of both sides. Okay, so we're going to have y equal to something, and it's going to be a mess. So what we can do, and it's a little counterintuitive, we're going to make it easier by taking the log of both sides, the natural log of both sides. Step 2, we're going to use the properties of logarithms to split up the really massive mess that is probably on the right-hand side of the equation. At that point, we're going to do implicit differentiation. Remember, that's where you treat y as a function of x. And so anytime you have a y involved in your derivative, you have to get a dy dx. Step 4, solve for dy dx. And finally, step 5, substitute back in for y. And so we'll see what this looks like here as we go. I've got a big, ugly example. So hopefully I can fit it on this board. Let's see. All right, so here is our example for logarithmic differentiation. As you can see, it took up my entire board, and so it's kind of a mess, but it is going to work out pretty much okay. I guess it depends on how well you like all the parts in it. So we want to find dy dx if y is equal to x cubed plus 4 times x minus 5 raised to the 1/2 power all over x plus 3. So this is a mess. Expanding this would be pretty much impossible, because of this 1/2 power. And even if it wasn't a 1/2 power, if it was say just a 5th power, it would really be a disaster trying to expand this all out so that we can take its derivative. So instead, what we're going to do is we're going to take the natural log of both sides. Perfectly legal. We know that if two things are equal, that their logs are also equal. And so then what we can do is the natural log of y is going to stay, but we're going to use the properties of logarithms to split up this mess in here. And what that's going to do is it's going to leave us with pieces that are a lot smaller. So remember, any multiplication, anything that's on the top will end up as positive logs, and you can always drop an exponent in front. So I have the positive natural log of x cubed plus 4 plus, here's that 1/2 that comes down, times the natural log of x minus 5. And then stuff that's on the bottom ends up as a minus the natural log of x plus 3. So it still looks like a mess, and I'm not going to lie, it definitely looks like a mess. But now we can take its derivative, and each of these little derivatives are going to be a lot easier, quite a lot easier than the whole thing would have been. And that's really the point of logarithmic differentiation, is to make our lives easier, or as we'll see with the next example, to sometimes make them possible. All right, so we take the derivative. The derivative for natural log of y is 1 over y, but again, because we're doing implicit differentiation and we had a y here, don't forget that it's then times dy dx. That's important, we got to have that. For the right-hand side, the derivative of natural log is, oh dear. Hold on one second, I'm going to fix some stuff. Sorry about that. I forgot to use the chain rule. Let's try that again. The derivative of natural log of x cubed plus 4 is 1 over x cubed plus 4, but then it's times 3x squared for the derivative of the inside. When you put that together, 3x squared times 1 over x cubed plus 4 gives me 3x squared over x cubed plus 4. The derivative of natural log of x minus 5 is just 1 over x minus 5. With that half in front, I just get 1 over 2 times x minus 5. And then minus the derivative of natural log of x plus 3 is 1 over x plus 3. These last two are nice because the derivative on the inside is just 1 for both of them. So we didn't have to have, like I did here with the 3x squared. All right, so that gets us here, but we really just want the dy dx by itself, so I multiply both sides by y, which gives me y times that whole mess. So that's close to being the answer, but now we're going to do that last step that I had listed. We're going to substitute back in for y. We just bring what y was equal to, we substitute it in, and there's our answer. Dy dx is equal to y times the mess we got from taking the derivative of all those logs. Now, If you're taking my class, it's entirely possible, in fact, it's very likely that your book will get a common denominator in here and use that to maybe clean up this just a little bit more. Honestly, I don't care. This is a great place to stop. It's not going to get that much better. Not really. But just know that that's what your book is doing a lot of the times when maybe you get this for an answer and it has something different. So that might be something to look for. Get a common denominator in here and see if you can reduce anything. So anyway, that's implicit differentiation. It's a mess. I do have one more example, and let's take a look at it on the next screen. Okay, so our last example isn't going to use logarithmic differentiation. But let's find f prime of x if f of x is x to the x power. Okay, so I first rewrote x to the x power. All this is stuff that is the work that I was doing to try and be able to do this. So we have a variable in two spots, both as the base and the exponent. We're going to have to be a little bit creative. So the first thing I did was I brought in e, because e is basically our best friend. So x to the x is the same as e raised to the natural log of x to the x power. Again, that's true because e and natural log are inverses of each other. I then drop the x down front, so now my function is equal to e to the x times the natural log of x power. And I can see that when I go to take the derivative, I'm going to have a chain rule because the exponent here is a mess. So I called the exponent u, and I took its derivative. So the derivative of that exponent of the inside piece here is going to be a product rule. So the derivative of x is 1 times the natural log of x plus x times the derivative of natural log is 1 over x. Clean that up. 1 times natural log of x is just natural log of x. And x times 1 over x is just 1. So when we took the derivative, we get f prime of x is equal to, well, the derivative of e to anything is just e to the anything, so there's that first part. But then we do have the times the derivative of the inside, which is great. And then I know that e to the x natural log of x is the same as x to the x power, so I just bring that back. And there we go. There's our derivative. It's kind of a cool one. So thanks for coming. Have a great day.